Have you ever really stopped to think about what happens when you flip a light switch? I mean, what is actually going on in there? Well, today, we're taking a journey into that invisible world inside the wire. We're going to start with just a single tiny electron and build our way all the way up to understanding the entire electrical system that powers our modern lives. So, let's dive in. So, here's the plan for our journey. First, we'll tackle the big one. What is electric current anyway? Then, we'll figure out the force that actually gets it moving. After that, we'll see how we can control that flow, how everything is wired together, and finally, we'll connect it all back to the real world, our power bills, and of course, our safety. All right, part 1. I want you to picture a simple copper wire. It's just sitting on a table, not plugged into anything. You'd think it's totally quiet and still inside, right? Well, not even close. On a microscopic level, it's actually a wild, chaotic dance floor in there. And this slide shows you exactly what I mean. On the left, in that disconnected wire, you've got billions of free electrons just bouncing around like crazy. Total chaos. They're going every which way. But here's the key. For every electron that zips to the right, another one is zipping to the left. The net result? Absolutely nothing. But then, look at the right. The moment we connect a battery, something amazing happens. All that chaos gets organized into a disciplined march. Every electron starts drifting in basically the same direction, and that ordered movement, that is the birth of an electric current. So that brings us to the official definition. Electric current, which we call I for short, is really just that ordered motion of charge. You can think of it like counting cars on a highway. We measure the current by seeing how much charge, or Q, passes a single point in a specific amount of time, T. It's that simple. More charge passing by in less time means you've got a higher current. So, these electrons are marching along, but how fast are they actually going? You'd probably guess they're moving at lightning speed, but check this out. Their average speed, what we call the drift speed, is just 0.07 millimeters per second. I mean, that is literally slower than a snail. So, that raises a pretty big question, right? If the electrons themselves are moving so incredibly slowly, how is it possible that a light turns on the very instant you flip the switch? And here is the brilliant answer to that puzzle. It's not about one single electron running a race from the switch all the way to the light bulb. Nope. The moment you flip that switch, an electric field pops into existence through the entire wire at almost the speed of light. The best analogy is a pipe that's already full of marbles. If you push a new marble in one end, another one pops out the other end instantly. The field is the push, and it gets all the electrons everywhere in the wire to start moving at the exact same time. Which, of course, leads us to the next big question. What is that push? What is this invisible force that takes all that chaos and gets the electrons moving in an orderly line? Well, that's what we're digging into next.
That push has a technical name, potential difference. But you and I know it by its much more common name, voltage. And honestly, the best way to think about voltage is just as electrical pressure. It works just like water pressure in a hose. You need pressure to make water flow, and electrons need electrical pressure, voltage, to flow through a wire. And what provides that pressure? A battery. It's basically an electron pump.
So how does a little battery create this powerful pressure? Well, inside there's a chemical reaction going on. You can think of this reaction like a bouncer at a club, physically separating the positive and negative charges and forcing them to opposite ends of the battery, the terminals. Now, as these charges pile up, they create their own electric force that pushes back. The battery is basically fully charged when that chemical push and the electric pushback are in perfect balance. It just sits there, holding that constant pressure, ready to get to work. Okay, so we have a force pushing the electrons, and we have a flow, but it's not always an easy ride for those electrons. As they try to move through the wire, they're constantly bumping into things. The material itself actually fights back, and understanding this opposition is the key to controlling electricity. And this fundamental relationship was discovered by a guy named George Simon Ohm. And his law is just beautiful in its simplicity. Ohm's law says that the voltage, or V, is directly linked to the current, I, and the thing that links them is a constant called R, which stands for resistance. Resistance is just a measure of how much a material gets in the way of that electron flow. And this little formula, V equals I times R, is truly one of the cornerstones of all electrical engineering. So what actually determines how much resistance something has? Well, it boils down to 4 main things. First, length. The longer a wire is, the more stuff the electrons have to navigate through, so more resistance. Second is the thickness, or cross-sectional area. A thicker wire is like a wider highway. It gives the electrons more lanes to travel in, so there's less resistance.
Third, the material itself. Copper, for instance, just naturally lets electrons flow more easily than iron does. And finally, there's temperature. For most metals, when they get hotter, their atoms vibrate more wildly, getting in the way and bumping up the resistance.
And understanding this is exactly why we choose certain materials for certain jobs. For the wires in our walls, we want the path to be as easy as possible, so we use a low-resistance material like copper. But for the filament in an old incandescent light bulb, we want the exact opposite. We use something like tungsten, which has a super high resistance. That resistance makes it fight the current, heat up, and glow brightly, turning electrical energy into light.
Okay, we've got a handle on current, voltage, and resistance. So what's next? Well, how do we connect things, like multiple light bulbs, together? It turns out there are two main ways to do it, and the choice you make changes everything.
So on the left, we've got a series circuit. The classic example is those old-school Christmas lights, right? The electricity has only one single path to follow. It has to go through the first bulb, then the second, then the third. And you know the big problem? If one of those bulbs burns out, the whole path is broken, and every single light goes dark. Now, on the right, we have a parallel circuit. Here, the current splits up, giving each light bulb its own private branch. And the best part? If one bulb burns out, who cares? The other branches are totally unaffected, and they stay lit.
So that leads to a pretty obvious question, one you can probably answer yourself now. Knowing the difference, why is your entire house, every outlet, every light switch, wired up in parallel?
Well, it really comes down to these three massive advantages. First, every single outlet in your house gets the full, powerful voltage it needs to operate. Second, you can turn on your coffee maker without also having to turn on your hairdryer. Each appliance can be controlled on its own. And, maybe the most convenient part, when that one light bulb in the hallway finally burns out, the rest of the house doesn't plunge into darkness. Parallel wiring is really what makes a modern home functional.
All right, we are on the home stretch now. We've gone from the tiny electron all the way up to the circuits in our walls. So for this last part, let's bring it all home and connect these ideas to things we see every day. The power ratings on our gadgets, our monthly bills, and, most importantly, electrical safety.
You've seen 100W on a light bulb or 1500W on a microwave. So what does that W actually mean? It stands for watt, which is the unit of electric power. And power is just the rate at which a device is using energy. We figure it out by simply multiplying the voltage it's connected to by the current it draws. A device with a higher wattage is just consuming energy at a faster rate.
And how does that connect to your monthly bill? Well, the power company doesn't charge you for power, they charge you for energy, the total amount you've used over time. The standard unit they use is the kilowatt hour, and it is exactly what it sounds like. It's the total amount of energy you would use if you ran a 1,000-watt appliance, like a really powerful heater, for one continuous hour. Okay, let's talk about something really serious: safety. What actually makes an electric shock so dangerous? A lot of people think it's high voltage, but that's not the whole story. The real killer is the amount of current that actually flows through your body. And as you can see here, it takes a shockingly small amount. Just 1/1000th of an amp, and you can feel it. At 70 thousandths of an amp, if that passes through your heart, it can be fatal.
And it's precisely this danger that's why our homes have built-in safety features. If you plug too many things into one outlet, they can try to draw more total current than the house's wiring was designed for. That's called overloading, and it can make the wires get dangerously hot. It's a huge fire risk. To stop that, we use things like fuses or circuit breakers. A fuse is an absolutely ingenious and simple device. It's just a tiny piece of wire that's designed to melt and break if the current gets too high. It sacrifices itself to break the circuit and stop the flow before something terrible can happen.
So, to wrap everything up, let's finish with a classic brain teaser to see if it all clicked. We have all seen birds sitting perfectly happy on a high-voltage power line. If those wires are carrying deadly amounts of electricity, how come the bird doesn't get shocked? Think about everything we've talked about.
And the answer brings us right back to one of our first and most important concepts. For a current to flow, you must have a potential difference, a difference in that electrical pressure. Since both of the bird's feet are touching the exact same wire, they're both at the same, very high potential. But there's no difference in pressure between them, so the electricity has no reason to take a detour through the bird. It's the perfect final example. It shows that to really understand electricity, it's not just about how much power there is, it's all about the difference.